Right, so let me start. Okay, so I'm a roboticist. So I do AI, but I do AI for robots. So I called it robot intelligence, but now everyone calls physical AI, embodied AI. So I'm using kind of a popular terms. And what I'm doing is mostly platform independent and also task agnostic physical AI. And as you can see in these examples, I've been using navigation as one of my main problem domains. And then recently I'm getting more arts as the problem domain. Okay. So throughout the talk, I'm going to repeat the same story. So creativity. And creativity to me has things to do with out of distribution, out of domain, and long tail. So you will see these recurring themes throughout, because creativity comes out of ordinary. So if we draw the sample from the most common distribution, we don't kind of find that creative. So okay. So let me use a very old example. So this is a project I worked almost 15 years ago. So the task was given this natural language command, navigate to the traffic barrier behind the building. So sending the robot to the back of the building, given a natural language command. And just briefly, imagine you are that robot. And when you open your eyes, this is what you see. Right? Okay. So is that a difficult problem to you? So for human, so I ran also a user study, like asked the same question, similar questions to people. And people just find it so easy. It's just easy. And then surprisingly, even if we don't see the back of the building, by the way. So it's the front of the building, but the majority of people come up with the same solution, very, very similar. So what's shocking, almost shocking, is how do we come up with this idea about the unseen parts? So the approach that we developed 15 years ago was kind of inspired by how human thinks. So human spatial intelligence includes these imagination. So being able to predict, being able to hypothesize. Okay, so it includes the seen parts, but also the unseen parts. But that was 15 years ago. So now that it's such an easy problem, we should be able to just get the answer right away. Okay. So I've been trying whenever there is an update. I've been playing with this example. So ChatGPT 5 just came out this summer. Okay. Do you think it's correct? It's actually incorrect. So I told the GPT, oh, no, 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 that's the left of the building. So I told you to go to the back of the building. And then kind of it modifies the plan slightly. I almost thought that these are identical, but they are slightly different, but both are wrong. Okay? So ChatGPT 5, the most recent model, cannot solve this problem. Okay? I tried another open source VLM, vision language model, and this is even more creative. Like it came up with this kind of a US map with something like a Russian instruction. Okay. So entropy Claude. Okay. So the version right before failed, but Claude to me is the most honest model. So when it failed, it actually said, this is such a difficult problem, I cannot solve it. And in order to solve this problem, I need a satellite image. And then it's also warned me, you know, the destination you're trying to go may be dangerous. Maybe it is in North Korea, so you may not be allowed to go. So, so Claude gave me a long list of reasons why I shouldn't even attempt. But the version that came out a month ago is able to solve this problem, like so suddenly. So I'm guessing they did something, okay? So I tried many variations of similar examples, and it uses the same kind of a method to solve the problem. So it knows how to do this. So I tried a similar example using an indoor scene, and it fails. So, and then the typical trend of the BLM is always put the target in the visible side. So even if it's in the back, it always creates something that they can see. But through a few iterations, I was able to make it work. So over time, maybe Claude will be able to solve this problem. So I tried something else. So perspective change. So given this same image, I asked it to describe what you see from the front. And it does a perfect job because it's describing what the image is showing. And then I asked the question, so if you're in the back of the island, what do you see? And it cannot do that. It's, changing the perspective, but it can only describe it just the same way as if it's still in the front. And then left fails again, right failed again. But if you see the illustrations, these change it. They try to modify a little bit, but still wrong. So these are the examples where these large, powerful models fail. Okay? So vision language model trained on understanding images, like the whole field of computer vision generally focus on how to process sensor data, like pixels, understanding the pixels, understanding the frames, but all the data that's coming from sensors. Like sensing is so central, it's so focused on, like it must be within what it can see. All right. So physical AI, the model, this is great. So it's trying to get the observation and then produce action. So something like a vision language action. It seems like it's the way to go. But what I'm kind of suggesting is it's missing something. Because when we make decisions, we use a lot of information that we can imagine, we can predict while our eyes are closed. So those are the part that I just generally called creativity. So, okay. All right, so to summarize this kind of long kind of a complaints about existing approaches, so the creativity may complement the sense information processing through this additional ability. And then the existing vision language model may still lack something because they are trained on sense data. Okay, so there was a complaint. And then in the next part, I will show some samples of what we do in our lab. So this is mostly related to the problems where there's no data. So it is kind of switching domains, so the models have no idea. Right. So using this simple example to illustrate the difference between just AI and physical AI. So I'm going to use this art as an example. So if we ask just a vision language model, just plain AI, for a portrait of Van Gogh, then we get the image. Beautiful. Okay. Because we have a lot of data in language and a lot of data in images. So the model learned to map the two, translate between back and forth. Okay. But if you want to have a robot to paint the same thing, like give me a painting, the real painting version of a portrait of Van Gogh, then that's tough, right? So because someone has to add brush strokes, one stroke at a time, and that's very hard. And guess what? There's no data, okay? So that's why it's a robotics problem, and that's why it's difficult. And also, like, look at it carefully. What the robot is holding is a brush, okay? brush has something like a hair, which is called a deformable object. It's very hard to represent that deformable object. And then the material, the medium that the robot is using is paint, which is kind of liquid and solid or in between. And depending on how much water you add, it's very hard to predict how the stroke will come out. So there is a heavy uncertainty. So whenever you take an action, you really don't know like what the canvas would look like in the next step. So that's very different from playing a game. Because even if you lost the piece and it gets knocked down, if you move your chess piece to like C1, then it's on C1. So there's no uncertainty. But in real world problems, there's always uncertainty, high uncertainty. Okay. All right. So that's where the difficulty lies in the robotics problem, like generally, and the type of research we do. So because our research produces these artifacts like paintings, some people think that, oh, you're doing an art project, but we are not. So we are still roboticists addressing difficult robotics challenges. So again, kind of imagine you are together with this robot that can paint. So the Prida is a robot, painting robot. So think about what you want to paint if you are painting together with Frida. So I'll give you maybe a couple of seconds. Okay. So you have some idea like inside your head. And then think about how you would communicate that idea inside your head to the robot. Or it could be a human painter. Like, how do you kind of pass that information that's inside your head to another agent? What do we use? Right? So we use language a lot. So we use text or voice. And between the two, which one do you think contain more information? Language, but in the text format or voice? Like comparing text messaging or voice call? Yes. Right. So the voice reveals a lot of things. So young generation in the back, I know you don't want to call someone because you can't lie about your LOL like emojis because so it reveals a lot more. That means if we use voice as an input, we can get richer information about what the user really wants. And sometimes we use kind of waving hands or drawings or sketch. Okay, so it's about painting. So it's maybe the composition. So I want the person in the center and then maybe a dog on the right hand side, something like that. So you can kind of describe the composition using a quick sketch. And sometimes it's too complicated, so you can't really describe, then I want something like that. So you can give a specific examples or a photograph of an item. So this list goes on and on and on because we use a lot of different modalities to communicate our ideas with other agents. So in the kind of technical term, this is called planning with abstract goals. Because the goal is specified, but in a very, very ambiguous, vague terms. So interpreting that to satisfy the user is a difficult problem. So in order to work with the humans are difficult to satisfy because they say one thing, but they mean something else. So it goes through a lot of iterations, but the end goal is to satisfy the user. So that includes creativity, compassion, and also safety. So safety, I'm going to cover like physical safety, but in this case, mostly like emotional safety. So a little more on Prida. So this is the research that we do. In like my students get PhD in robotics. So one of the PhD students who did the painting project focused on reducing the gap between simulation, what's inside the head, and what happens in reality. So, so just very quickly, some of his ideas early on, it was the very first idea was a handcrafted rules. So my robot can only do this, so the constraint languages. And then the little bit of a milestone that happened was using the real robot data to train differentiable renderer. So like earlier, you learned what that means. So it is still model-based, but we use the real robot data to tune the renderer so that the simulator can generate the target that the robot can actually feasibly paint. So, and then the latest model was more focused on the freestyle model. So again, because it's a model-based, if you change the model, we can also address different problems. So, okay. So very quickly show the result. So in 2019, the very first one, we used somebody else's approach. There was a reinforcement learning based approach that generates a very nice painting. So we used our very, very tiny robot to paint. And then we got it. So we were so excited. Wow, this is a real painting. But why is it so different from the simulation result on the paper? So we realized that that simulator has no idea what kind of robots we are using. So all the robot limitations, constraints, the environmental setup, there's no connection. So the first one was the handcrafted constraints. So the simulator quality went down, but the overall real-world painting went up. And then the next one was using that real-world data to train the better simulator. And then the last one was a longer stroke. So we changed the model to support the freestyle full spline model, which was the latest one. And like from this 23 model and on, the differences in the final outputs are kind of subjective. Some people still like the older one, but the details are the difference. So in the last one, if you notice, the person is wearing glasses, and this is the first time we are seeing the glasses in the painting. So, okay. So this student graduated, so defended his thesis just weeks ago, so I'm very excited. And his last chapter was applying this idea to 3D sculpting. So in this model, it's just a kind of a very preliminary showcase on how we can use this same idea in a very long horizon deformable object manipulation task. So if you're not familiar with the deformable object manipulation, these alphabet making tasks are like still very, very early stage. So there are papers that use maybe 3, 4 gripper actions to make X or maybe B. So that those approaches are very different from what we do. We are really taking a long number, like a large number, more than 400 actions to get to some shapes. So this is a promising direction that we will continue. And then, so deformable object, so we like these difficult tasks. So that includes higher uncertainty than rigid objects. And so this is another example of a deformable object manipulation that's also producing the artifacts like pottery. So, and then this next two example is at a still early stage project, but I'm going to show it. So generative AI, even if it's really, really powerful, they have a difficulty in taking constraints, like what not to do. So in this case, these are the actual like puzzle pieces, so wood blocks. So if we ask the model to use only these shapes to create something, then we get a kind of entertaining results. Okay, So for the approach that we developed, we take the constraint reasoning together. So this, I'm gonna kind of skip, but the limitations of existing generative AI models. So like if we kind of ask the model to, okay, use only these and do not modify the shapes, but it cannot really follow that constraint satisfaction. So for instance, the first one, ChatGPT ones, from far away, they look amazing. But if you look at them carefully, they modify the pieces to make it work. And then the third one, it's for the horse. And in the original block, there is a piece with a Korean word meaning star, 별. And the model changed that to a Chinese character meaning horse. Yeah, so that's kind of cute, but you know that's wrong. And instructs to Pix, it doesn't know, so it just adds a new object there. So this remains a difficult problem. And this is a kind of a general limitation of existing trendy approaches that only take positive examples. So taking negative prompts sometimes works, but it's not really fully enforced. So taking hard constraints are hard. Maybe it's because hard constraints. Okay. So, and then the next one is, again, kind of using creativity to generate scenes. So earlier in the morning, we saw how to generate the full shape or changing lights, but kind of think this problem as a larger scale. So we want to be able to generate the space. So if you watch the movie called Inception, you know, those architects, they are great in generating new spaces. But what's difficult in the, So what's difficult in this problem is making them in 3D consistent and also RGB consistent. Because if you keep generating the nice videos, they look amazing, but you can never come back to the same place. So that this is the most recent results there. Okay. So am I still good with the time? Okay. So yeah, so the next part, I will focus a little bit more on the nuanced problems. So maybe it's from the same distribution, but it has a really long tail. Okay. So, all right. So in the safety critical domain, this problem is really pronounced. So autonomous driving, the industry kind of sector started more than 10 years ago. So data, the quantity-wise, they have really a lot of data. So when we use their data, we subsample because there are just too much, okay? But the data we need, there is none. So this is an example of a crash. So autonomous vehicle failed, like it just stopped in the middle and then created a giant case. And then this is even a rarer case. So there is a small delivery robot that is going to be hit by an autonomous vehicle. So the very first premise that started this autonomous driving industry was it will be safer, but the statistics is showing it's not. There is actually a lot of accidents by autonomous vehicles, so we need to make it safer in order to be accepted, right? But there's no data. So the Argo did an amazing contribution to this research field by providing gigantic data set. But guess what? In that data set, how many kind of accident data, the real crash? 0. Yeah. So that's why it's difficult. So Ben, another student who defended yesterday before I came. So Ben, I don't have time to go through all the different approaches, but Ben developed 4 or 5 different ideas how we can leverage existing data set and also cover these safety critical ones. So the very first one is creating this filter so that we can scoop kind of maybe those are like close enough. There's no accident, but it could have been kind of a counterfactual reasoning. And then the later models are more compositional so that it can really synthesize new incidents, but they are also kind of more likely. Because if you can just generate very random like scenes, that's easy. But it's also garbage because it's never going to happen in real. Okay, and then very similar setting, but in airspace. So many people think that airspace is kind of not very dangerous because it's like if there's so much free space. So what's the chance two birds will have a head-on collision? So during the midair, it is rare, but it does happen near airports. Because whenever you are kind of taking off or landing, airport is an extremely busy space. And then in the recent years, like past couple of years, we are seeing finally on these on the news. But we've been watching these data for years. So we warned the people, okay, it's not really safe. There's so many near misses. And near misses never makes the news because there's no accident. But there was a New York Times article that revealed so many near misses, and one of them has like three-way incursion, which is very scary. And then there was a final, like a fatal accidents, couple of them, which is really sad. So we want to make this space safer. So we created this large data set, and then we are going to apply similar ideas to make even more useful data to include the safety critical cases. Okay, and then a slightly different topic. So in image generation, there is also like the part that's lacking data. Because image generation is so good, so good. Like image editing, everyone is using it and everyone is happy. But some people, it's kind of interesting how we even don't realize how we are represented. So like the Asian countries or Africa. So as you can imagine, it's the curve again. So smaller countries are not very well represented in the space because there are like fewer data points. So whereas we see a really, really sharp increase in general performance, Sora, like video generation, they are amazing now. But we've been watching this culture bias from like several years ago, and that curve is still pretty flat, so especially on open source model. So these are some of the examples. And then for neutral prompt, if you don't specify the country or what culture background, you get US. Like it's just America. So like North America. So it is a very, very biased. And some of these closed models, they must have done something. So the latest model can create really nice Korean images. So we had this meeting, okay, maybe we don't need to continue this project anymore. So we were about to celebrate and then realized, oh, not yet. So maybe one more project. So if we ask a little bit more specific example, they still fail because the way they fixed was they augment the text prompt using very, very specific descriptions. And then sometimes the descriptions are all good, but the model doesn't fully understand. So this is a 붕어빵. 붕어빵 is a fish. So the description says it's a kind of cookie, looks like a goldfish. And then it's made of egg, so it puts the egg. And in the other example, it really put the like bright orange goldfish. So so it failed. And then the first picture there is about Hangulal. Hangulal is a celebration of a Korean letter system. And then the banner is in English and the person is writing something in Chinese. So, and then these are for Chuseok, like the Thanksgiving kind of an event, and the dishes. So, there are still, there are room for improvement. Okay. And then we also check the gender and racial bias. This is a well-known problem, but the thing is, it's still there. So any male person here who wanted to become a model, like, you have zero chance here because it's all female, like 100%, and and also a chef. Like in order to be a chef, you have to be a male person. So it's very heavy bias. And then the skin tone, you probably don't see the numbers, but the light region is the light skinned people. So we are like in the small portion. So, this kind of like wraps up to existing bias and where the models still fail. So it's kind of a little bit outside, but it matters because we are also part of that minority. So, and in many aspects, many like perspectives, you fall into some sort of a minority region. So we can't just work for majority, which is how the data-based approaches work. So the last portion is why we are doing this. Like why we are doing this AI research, robotics research, because we want to help people. So the human robot collaboration part. So when we developed a robot that can paint, people were always asking, are you going to replace like a human artist? The answer is no, because first of all, the robot doesn't really do a good job. So it's not that good. So, and then it encourages people. So the other example is we did the demo. We have done a lot of demo. And then whenever we do a demo, this was at a hospital, therapeutic, like the therapy session. And whenever we ask people, hey, do you want to paint with our robot? Their answer is no, 100%. Like, okay, I'm not a painter. I don't know how to paint. When was your last time, like, did a painting? Yeah, you don't remember, like third grade, right? So people are afraid of like starting, but when we ask, hey, do you want the robot to go first? Then they say yes. And then the robot starts painting, and really magically, they all say, hey, give it to me. That's not what I meant. Okay. And then they just have fun. And then they also talk a lot with other people in the scene. So they socialize. And by that time, robot is not even there. Like robot is doing something, but they don't care. So robot's role, the biggest role is that starter, catalyst. They don't want to do it, but the robot kind of encouraged them to start. And the true health benefit, like whatever benefit they're getting, is by doing it themselves. Like watching someone else like playing soccer doesn't make you healthier. But when you play soccer, you become healthier. So robot can encourage people to create more arts. And then the physical interaction. So I think there was a lot of discussion, like when we will see a lot of robots around us. So some people projected to be maybe 5 years to 10 years, like 10 years for sure. There was a definite answer this morning. So I think a lot about human safety because I've been using robots for a long time and I know they can kill us. So even the smallest robot, if they don't have a sensing, it can really crush your hands. Like, they don't really have the sense, right? So they are powerful and, they dangerous. So how do we make robots safe, physically and also emotionally? So we develop these soft robots that can be on top of rigid robots. So these were like fun examples. We did it for Halloween. And then these are actually robots. So inside the robot, there is a camera sensor that can see. So if someone touches, then the robot can actually feel where a person is touching so that they can interact or they can be more compliant. So, and the project started with this one finger. So probably you have seen the hair manipulation. So we got an IRB, like human user experiment approval for touching human's head because the robots are soft and hollow. So, okay. And this was more like art project. So far these are more hardcore robotics project, but this was for arts and robotics session exhibition. So this was more of a story that we were sharing with the community. So we designed that small robot that is interactive. So it has a proprioception. So if someone touches, then it can react. And we put this small robot inside the giant inflatable. And then when people are interacting with this small robot, they will notice the outer layer react. So if you touch this side kind of lights up. So we wanted to give the users that kind of feeling. So you are interacting with our system, but you will, from outside, but you will feel like you are inside the robot. So this is more like our like promise. We want to make the system that's transparent and explainable to the users. Okay. And then for this safety, so human robot safety. So this is another kind of an art show that we did it at the Humanoids Conference this summer to introduce this concept. So robots, between humans and robots, what is the layer that we need to provide? So this was a kind of conveyed through the form of fashion. So robot is wearing these actuated like airbag kind of a thing. So to me, robots are like vehicles, cars. Cars have airbags. So at some point in near future, maybe there will be some regulations to ensure safety around robots, and also especially the ones that will be around human. And this is also to raise that awareness. Not many people think robots are dangerous, especially if they look cute. Looking cute doesn't mean that they're safe. So, okay. Okay, so in conclusion, so we are building compassionate, safety-aware, and creative physical AI to work alongside humans, collaboratively creating flourishing experience in the physical world. So the flourishing experience is more than just survivor. So we need the meaning of life, and we want to use technology to support that. Okay, on that, thank you.
Thank you so much for your talk. All the projects that you presented today look so fascinating. Question from the audience?
Thank you for wonderful talk. So actually, I always wondering that. So is there any special way to get some inspiration for your creative AI? So like some going to museum, watching some musical performance, something like that?
That's a great question. I mean, it comes from like every day experience. So sorry. One of my students started working on making pasta, handmade pasta, and they came from my trip. So I had a trip to Italy and I took a cooking class for the first time in my life. So I never had a cooking class, and it was making pasta by hand, like mixing flours, and you really make it just like, it's similar to making sujebi in Korea, but it's using tools. So I thought that was a great example. So we started doing it. So that was one example. And then also the puzzle. That was the wood piece that my daughter used to use. So I bring all the toys to the lab, and then students play with it, and then the robots start using it, and then we have a project and the pottery project too. So I just bought a pottery, the spinning tool, and then I ask the students, hey, if anyone is doing a robot project with this, then I will support. Then sometimes the students like the idea and then starts. And then I also ask so each student what their passions are. So like the what they really are truly passionate about, like when they're not working. And sometimes you will get very, very nice answers. And one of my students is a ballet dancer, and he's great in understanding human motion because he's a dancer. So I want to connect his passion with his project of making robot hands. And then another student who just graduated, Ben, his research was mostly about the trajectory prediction, and now he's doing the final project with music because he's passionate in like music making. So and music is also sequence to sequences. So yeah, so those are yeah.
Yes, there's another question there.
Naming Frida as such is quite intriguing to me. If I'm not mistaken, you name it following Frida Kahlo.
Yes.
So can you introduce any anecdotal episode when your team decide to name it as such, if any?
Yeah, so Frida, when we started the robot painting project, we didn't have any like decent robot, and we heard the rumor somebody so and so is throwing away their old robot. So we picked it up and we fixed the robot. So that was our first Frida robot, and then without a name, and then I just thought about Frida Kahlo because she went through a lot of pain and difficulty in her life, and so let's call the robot Frida, and everyone liked it. So Frida came as a robot name, and then when we wrote a paper, I just turned that into an acronym, and it's a framework and robotics initiative for developing arts. So it kind of came out perfectly. So, and also we play with a lot of names. So for Ben's project, the trajectory prediction, one of his approach was a emulation. So yeah, that's an acronym that I suggested, but he didn't take it. So yeah, it's like a lemur because it's a long tail. Yeah, but that he wanted to call it like long comp.
Okay, other questions? So I have one last question. So you've been working with robots for a very long time, right? And there are a lot of people that are getting into robotics now. And CMU has Robotics Institute, and they had this department forever to me. So in your expertise, as a long expert of robots, same question to yes. Do you think we'll have robots going around and doing its things within the next 10 years?
That's a great question. So my hope is within 5 to 10 years, and I use this X curve. So X curve, one is going up, one goes down. One is going up is a very flat, and then in the past couple of years, I see kind of going up. That's the capability of a hardware. Hardware is getting better and better and faster. So I saw the tick going up. And then the other one is the price. So even when the robot is doing nothing, it was so expensive. That's why I didn't have any robots. So it was so expensive. And then the price is going down. So now we are still at the point that robots are not doing much. but still expensive for normal users. But they will meet soon, like in a few years. Then it's the intelligence, so that's why many people are investing money, and just based on like prior experiences and what happened in the manufacturing setting, even if we don't have the generalist like perfect robots, there will be usable robots. That's my like
Thank you
guess.
for the great answer. Thank you so much. So let's thank Professor O once again. And we'll have a break for 30 minutes. And so the next session will start at 3:40 p.m.